Hi, this is Shelly Physics. I'm doing a quick supplement video for getting charge up activity. You should be able to go through the section 1 and hopefully you have a balloon for section 2 or something like that. I give a few other options there like styrofoam. That works great, so try that out for section 2. Now section 3, please read through that carefully. It's going to talk about how charging through friction works, and we're getting into a section on what's something called the law of conservation of charge. Law of conservation of energy and matter works very much the same way. The big idea is that the charges you have to start with equal the charges later on. So if there's some kind of interaction between objects and charges redistribute, you gotta remember that the number of charges that you start with equal the number of charges that you end up with. So in this section, please read through it first, look through the example. Take a moment now, pause this video if you wish. I do encourage you to do that. Okay, I stuttered there to give you some time. So here's the idea in this example. If you have a conductor, let's say 2 conductors that are exactly the same kind of size, same kind of material, they're identical in all respects, except for the first spherical conductor, has 6 negative charges. The second one has 0. It is neutral, meaning it has a lot of electrons and has a lot of protons, and they're just the equal number. So the one on the left would be like an object with, let's say, 6 extra electrons. However that happened, it has, let's say if it's got 10 protons, it has 16 electrons. Okay, that just means it's got an excess of negative charge. The one on the right, let's say it has 10 protons and 10 neutrons, so it would have a net charge of 0. 10 plus positive 10 charge plus a negative 10 equals 0. So before an interaction, it's got a net charge of -6. And let's say they touch here in the middle, and then they're separated again. What will the new charge be? It'll still be 6. The net charge will still be 6, -6. But they're going to be redistributed. So these are conductors. So when you touch them together, remember electrons repel one another. So they're going to push as far away from each other as possible. And they're going to distribute evenly throughout each of those objects. Now, if you touch them together, they become one conducting object. So the electrons will spread out evenly throughout both. So when you separate them out again, that neutral charge, the neutral object on the right, will now have some negative charge. It'll take 3 of those negatives and leave 3 behind so that they're equally distributed. Now, if you had one object that was much larger than another or made of a different kind of metal, they're definitely not going to distribute in equal numbers. This would be for identical objects. That would be the advantage of having identical objects. But the main point here is that the net charge remains the same, and after they touch and are separated again, they're now of the same type of charge. They're both negatively charged, so they'll actually now repel. You see beforehand, a negatively charged object and a neutral object will not repel or attract. After they touch and have charges here, they're going to be repelling. But each one will now have -3. So this one started with -6, and we had 0 before, and now they're both at a -3. Both sums equal -6. Okay, that's the main point here. All right, now in reality, something does happen when you bring 2 negatively charged objects together. If they're conductors, there is going to be a little bit of induction that goes on. Those electrons will tend to move towards opposite sides. And so there might be a redistributing of charge. So after they touch, they will definitely repel no matter what. Before they touch, though, the electrons that might be usually hanging out on this side of the sphere are going to leave their proton behind and transfer to the other side. So kind of a unique thing happens here. There's going to be induction happening. Notice that the total charge on the right sphere is still 0, 3 positives and 3 negatives, but they've just redistributed, and that creates a surface close to this negatively charged sphere that is positively charged. So this cool thing happens when you've got a neutral object and a charge object is first they actually attract together, then they touch, they kiss, and then after they touch, they'll have an equal number of charges, so therefore they will repel after that. So it's this neat thing that happens. They're going to attract and then push away and repel and never want to see each other again. It's kind of like a bad first date. Haha. So your objective here is to figure out the total charge first. 2 plus a -4 is -2. And then think about how they're going to distribute afterwards so that the total charge will still be -2 after. And likewise, give it a go for these other two examples. Now, if you would finish up that section, pause this video, and actually I'll go ahead and work these out here in a moment, but pause this video, try it out on your own, and then come back and check it. Okay, hopefully you've had a chance to pause that. And so if we have a +2 and -4 has a total charge of -2. Afterwards, they're going to have a total charge of -2 as well, but they're going to be evenly distributed, like up here in this example. A -6 evenly distributes -3. So basically, we can take that -2 and divide it in half to get a -1 and a -1. That's how it'll work out. You might be asking, Mr. Shirley, what if you've got like a -3 to start? What if this is +2 and -4? Could you get a -1.5? I mean, what's a half an electron? Now remember, in large objects like this, they're made of uncountable by people. It would take a lifetime to count the number of protons and electrons in these objects. So we're talking about a large number of tiny, tiny protons. 1 coulomb of charge is like 10 to the 19 electrons, you know, somewhere about that order. The charge of an electron is the elementary charge, -1.6 times 10 to the -19 coulombs. So a whole number, a large number of electrons is involved here, not just one. So we're talking about one unit or one group. This could be 1 times 10 to the -9 coulombs. And we can, of course, break 10 to the -9 coulombs up in half, and that would be like 5 times 10 to the -10. That would be a half of, or 0.5 times 10 to the -9. So we can have 1.5 or 2.5 because this would have, it's not just a number of electrons or protons, it's the amount of charge that we're breaking up. So this next one, -1 and -7 gives us a total net charge of -8. That means afterwards it should still be -8, but redistributed evenly for -4 and -4. And the last one, there's a net charge of +4. -1 plus 5 is +4. So it should have a net charge of +4 after, and individually a +2 and a +2 would round that out. Okay. Again, just a little important thing to note, these would be for very similar or identical conductors. This is how it would work. If they're insulators, charge does not distribute or redistribute this evenly, and they're not going to just do this instantaneous balancing of charge. This only really happens with conductors. And the equal amount on each side, like -4, -4 for this middle one here, that does happen with identical conductors. So you just want to make sure you have the same mass, same type of metal, and that'll work out really well. If one of these was much larger than the other, it would likely hold more charge than the other. So it's not going to distribute exactly evenly. This may be more like if this were much larger than this one, it might be more like a -6 and a -2 or something like that. All right, so why does all this happen? It's all because of the electric Coulomb force, and that electric force is related to a concept called electric field. So if you're able to try out this section 2 up here, and you might have felt an effect of an electric field acting on your hair. You might have had that sensation of an electric field. So an electric field is an area around an electrically charged object that influences or forces other objects that are charged around it. So please read through that knowledge bit there. What we're doing is modeling the electric field in what's called a field diagram. So one unique feature of this is electric fields are drawn with arrows with vectors that point in the direction that a positive charge would be forced. Now, something about drawn fields like this is the distance between field lines represents the strength. So larger distance is a weaker strength. Closer distance between field lines is a stronger strength, stronger magnitude. And what we're seeing here is really the inverse square law. If you think about, let's say, a distance here, if we try to get an equal amount of radius, it's not a great circle at all. But anywhere around, if this were a circle, the field strength would be about the same. You see the distance here between those lines is the same as distance there. It's supposed to be about the same distance there. So that's the same strength. If we double that, we're going to get a much larger distance, and it involves that inverse square law as far as force goes. Okay, so that's the, this is just an awful sketch. Anyhow, we're not drawing circles around. I was just trying to demonstrate the distances, but what would happen if we, I didn't talk about this one, the negative charge would have same kind of field lines, but they would have a direction inward. So negative charge has an inward arrows, and positive charge has outward facing arrows. So what would happen if we bring a negative charge close to a positive charge? What would the field look like close to them? Well, we might start out just by drawing some short arrows, just like you see in these diagrams. Okay, for the positive charge, arrows going outward. Please do that on your own paper. Get a feel for drawing these field lines. They're going outward like this, okay? And with a negative charge, you'll have some field lines going inward, just like this. Now, usually I just draw, for the inward ones, I like just drawing the lines like this. I like drawing the arrows a little bit further out. Otherwise, it starts to look like a snowflake a little bit too much. Okay, so we got these inward field vectors. Now, how are they going to interact? You see this field line here? It's going out from the positive. There's another one that actually goes in towards the negative. Well, they're actually going to connect. And now, before I do anything else, I'm going to bring up a scenario with some magnets. Some magnets create a magnetic field very similar to an electric field. It's just a lot easier to see. So I'm going to take some bar magnets and put a piece of paper over the magnet, and the north and the south side of the magnet are going to be very similar to the positive and negative point charges right here. What I'm going to do is shake some iron filings over top, and they're going to form the pattern that would actually form here with this electric field. So let's check that out. So right here I'm going to switch over to the screen so you can see the north side of the magnet's over here and the south side is over on this side. So I'm going to put a plus right there and a negative right where that south side is going to be. And I'm going to place this underneath the paper. I've got these iron filings. It's going to sprinkle on top. I'd like you to see if there's a pattern that emerges. So those iron filings are lining up with the magnetic field lines between these positive and negative charges. See how, like in the middle, there's a lot of this linear kind of motion. The field points from like the positive to the negative over here. Get a few more in there. There we go, right in the middle. Okay, so straight across, that's what we're kind of seeing over here in the video. Let me switch back. Okay, so right in there, we're seeing that right in here. This middle part here, from the positive to the negative, goes straight across there. All right. And above, we see it kind of arching up, arch below. You notice it gets like really high or really low down here, or really high up here. If we add a little bit more, you can see that might be more impressive there. You can see the shape. Okay. Look at that up and down. Now to the outside, see how that spreads out on that side and how it spreads out over here. Okay, so those, they kind of swoop out. Now, all right, so that's it's kind of hard to see out here. It gets very weak. But way up here It actually does kind of curve around a little bit. It's just very weak. It's hard to see that action up there. So let's finish this up. All right, so where do these go? Instead of going straight up in that direction, it's going to kind of go up and then curve down into that line, and the positive is always going to go away and in towards the negative. So go ahead and draw this on yours. This one's going to kind of curve way up here, and it may actually curve back down like that. And likewise, we'll get the same kind of thing over here. Some symmetry going on there. And for this negative line, we're going to go straight out. There's no curving there. Now for these other ones, think about like a positive is attracted to the negative. So just follow along this pattern. This one's going to kind of scoop up kind of toward the negative, but not, it's probably unlikely that it'll really reach all the way around. Well, if we had a strong enough field, it would. Strong enough couple of charges. And these would swoop in the same kind of way. Okay. So that's kind of what it looks like. Next one, we're going to start out with these positive charges. Now on this one, we'll start out with the arrows again going up and out. But do one thing to make the drawing of this one a little bit easier in the end. When you get to that single line, that single arrow that you draw toward the other, split it up into two arrows instead that are just slightly off axis. Okay, so make this one just a little easier to draw in the end. So make a couple of them. Don't go straight out. They're representing the one, but I just want you'll see why here in a second. There's also going to be the diagonals, and then one going straight up, straight down, diagonal out on this side, diagonal that way, and just one straight out the back. You'll see here in a moment. So what if we have two positive charges? So in this case, what I'm going to need is a couple of magnets now. Here's the one. I'm going to need to switch this over. Just scooch it over here a little bit. So there's the north side of this one. I'm going to get a second magnet. So here I've got the two north sides of the magnets. You can see they repel each other. The north and south attract. So I'm just going to turn that one around. All right, now we're going to try to position these. All right, now we're going to do a sprinkle test. It's a little something different here this time. These are not sprinkling too well. All right, what do you see here? So the lines are starting to come out as they did before, but look, they don't curve together. They're curving away. These go swooping up here. This goes swooping up. These go swooping down. They're kind of swooping down and away, and there's a lot of linearity here. You'll see kind of like a lines going downward here, like in this direction. You can see these lines over here going upward over here, upward in that direction. Okay, and out here they start to curve down and left, up here down and right. Okay, up and left, up and right. So these are curving away from each other. This is sort of like if you have two hands, you kind of put your hands together like this and you start pushing, and your hands start to separate and get further and further apart. That's what this pattern looks like to me. We had these coming together, but then they were swooping up, and there's a lot of like change in direction there, different directions. And these, instead of coming together straight away, they swoop down and away from each other. So it is like your fingers being forced together. Makes your hand kind of stretch out like that. And these will not curve as much. They're field lines that are further away. And still they'll swoop down, not want to touch. And these vertical lines, instead of going vertical, and they're not going to go towards, remember positive and positive charges have a repelling force. So they're going to be swooping away from one another. These are the patterns we're looking for, swooping away. So this is just an introduction to electric field. Tomorrow we're going to, in the next lesson, we're going to see a lot more about electric fields and some different patterns. Try to get those patterns emerging more. And these lines out here will go straight out. You have nowhere else to go. If you've never seen that iron filings test before, I hope you enjoyed that, enjoyed seeing that. Kind of neat seeing those patterns emerge. But good luck on finishing this. Please read through the rest. Make sure you read through all that. There's some good extra information in there. And that's the lesson. We'll wrap it up.